When we're looking at the graphs, this is the one from a past paper question again. Please make sure that you read your question carefully. So this was given as a percentage, and then you had to go and work out the absolute uncertainty. So it's just the percentage of that value, and the absolute uncertainties were given. Then what you do is still as you would do it in normal physics, core physics. In further studies, you would do the same thing. You would still go and plot your values. Make sure you choose an appropriate scale. Do not use weird numbers like 4s and 3s. Because there are 5 blocks here, we like values that can divide by 5 and actually give you a nice number. So that means 3 divided by 5 is going to give you a fraction. So we don't want that. Please make sure that you write your scales on both sides. And if there are powers of 10, remember to include them on your graph, because you're going to need them later for your calculations, definitely. So if joules is fine, you don't also have to write big, you can just go EP, you don't have to write potential energy again. Your heading already has that. And remember, there is a video on graphing and specifically that I've shared with you about last year's paper. There's always going to be y versus x when you write your unit. Whatever is on the y-axis versus whatever is on the x-axis, and keep it simple. When you do your error bars, please remember that it's the actual error that is important. So the uncertainty, the plus minus. So these values those two sides is always going to be the same. Then that little sidebar, some people are making them very big. Please don't do that. Make a huge sidebar. I'm going to make this a little bit bigger to show you what I mean by that. If you make a huge sidebar, that is not part of your uncertainty. So some people want to make sure that it fits. So like for this one, they would make it long like that and then say, okay, I can make my line a little bit steeper because then I can make it fit in there, and then do a line that looks like this. So my worst acceptable line, they would then go, let's make it a bit higher because it's still touching that sidebar. That would be very wrong. It has to touch the line that represents your actual uncertainty. Make sure that you label your line of best fit and your worst acceptable line of fit. Normally only 2 are asked, but you can always do the third one if you want to. You can go and get your flattest line and your steepest line, and then your best line would always be in the middle of those two. But you don't have to. The question generally just asks for one of them, and then the uncertainty would just be the difference. We're going to get to that now. There was something else I wanted to say. Please don't force the line through 0. If your line of best fit goes through 0, that's perfect. So you can see the trend here is passing through 0. So 0 is a point. But don't force it through 0, because there sometimes is, if the equation that you are using in the end for the analysis, and you can determine that in your reading time already, if the equation has a plus or a minus, remember your ultimate goal is to write this in terms of y equals mx plus c. So you're going to find an equation that in the y position has an EP, sorry, that's just rain in the background, EP, and here that's going to be your gradient. But in your x position, so it's changing y over changing x, in your x position, then we're going to have our x squared. And then sometimes there is going to be a plus c. In this case, there was nothing. So make sure that you don't force it through 0 in case there is a y-intercept there. If it's close to 0, chances are it's going to go through 0. So don't also force it to not go through 0, because that would also be wrong. Alright, so that is the error bars. Make sure you draw them accurately. Make sure you don't make those sidebars long. Then when you need to go and get the gradient, I'll get back to that one just now. I just wanted to use one, and I think this is the one that is actually in your notes that you have. But for the gradient and the y-intercept, once you have your gradient and your y-intercept, so now you've drawn them perfectly. Look, that one is a little bit on the brink, and that one is a little bit on the brink of touching the sidebars, but they are still touching the actual error bars. Make sure that it does. So you can have a steepest gradient, which is that M2. M is our line of best fit. That is our gradient of our line of best fit, and M1 is our the flattest line, the most shallow gradient. Now, if we have a graph like this, you can say, I'm going to use the gradient of M2 minus the gradient of M1, and then to get the uncertainty, I'm going to divide it by 2, because then we've got that big distance there, so I need to divide by 2. So please remember, if you're doing that, you're going to take your steepest one minus your flattest one, and then you're going to divide it by 2. But if you didn't get both, or if you didn't draw both, and you only have your line of best fit, then please don't divide by 2. It's a general mistake that people make. Then you're just going to say M2, the gradient of M2 minus the gradient of M, and that will give you your uncertainty in your gradient. Or you can say, if it was the flattest one, then you're going to say M minus M1, and that would then also give you your delta M. And please then don't divide by 2, because that's already the uncertainty. The same with the gradients, with the y-intercept, sorry. Same with the y-intercept. That minus that would give you your uncertainty in your y-intercept, so your uncertainty in your C value. And or you can use the 2. If you use that big gap, then you have to remember, then it's going to be the C value of M2, so C of M2 minus C of M1, and then you're going to have to divide that by 2, because then you're using the 2 worst lines, okay, worst acceptable lines. Just remember that. Don't divide by 2 if you don't need to. Don't force it through 0, but in the past papers, often in the further physics, the line has been a direct proportion, because you don't have many equations with pluses or minus in it. Doesn't mean we can't find one, so you could have one. So in this one, this is on the video that I've also posted for you. So yeah, you could divide it by 2, or you can just use biggest minus smallest divide by 2. So I'm not going to focus too much on that. The one that was in last year's, so just showing why I did this is actually, some people still, although it's part of core physics for a while, some people still struggle with the analysis of this gradient. Once you have the gradient, then you need to go and find an equation. Normally the paper would say to you, use the gradient and a suitable equation. So if we go back to this graph, so now you've drawn your graph, you've got your gradients, you've got your y-intercept. The questions were asking that. Please then don't look at the graph again. So you've calculated and definitely don't look at the table of results. So let's just look at this one. They're telling you that for that line there, the y-intercept was given as 31, and for M1 it's 30.8, and for M2 it's 30.7. So if you wanted to get the uncertainty, as I already said, you could do the 2 divide by minus the M1 and M2 from each other and divide by 2, or just that. It's going to give you the exact same answer. But now, if the question now asks you for something specific, so they say it's not just a quantity. Let's say here we've plotted delta x or s, so I'm just going to use that, so that becomes my y equals, and then they tell you that here you've plotted for instance, let's say delta t, so delta t squared, or t squared. The delta for t is not really needed, so you can just say t squared. We've plotted t squared there. So that means in your x position, if we go y equals mx plus c, I need to change this equation into that format. So this will be delta x is equal, on my x-axis, I have now plotted t squared. We can also use the first equation, it doesn't really matter. Plotted t squared, so then here you can see half a is there with t squared. And then I have a plus ut there. Now, this is maybe a bit of a bad example, but then what you should see from this is that because I plotted delta x on my y-axis, the method here is important, and I've plotted t squared on my x-axis. Now, clearly it should shout at you that my gradient, so don't go back to your table, don't go back to anything, your gradient is going to be half a. So you've already got your gradient, you've calculated it, and the question says use your gradient. I've got it here, use your gradient, and they told you here that the gradient is 1,06. So then you're just going to say half a is equal to 1,06. If there were powers of 10, yes, you need to add them in. But don't go and make up other things. Don't go back to the table. Don't substitute a point. And then you're just going to say a is then equal to 2 times 1,06. And that is going to give you your answer. And that's quick and easy. And then your y-intercept, I should be using different colors here. So that is how we got our acceleration. And then your y-intercept would be equal to ut. So that would mean again, don't go back to your graph, don't go back to your table. We've got our y-intercept here already. So we're going to say ut is equal to 31,8. And they would probably tell you either what the initial velocity is or what the time is, and then you just substitute it in and you just get that value. You don't try and make weird things out of it. You don't go back to the table. You don't substitute anything. Please, that is very, very important. So you will see that from the one that was in last year's past paper as well. I'm just going to quickly show it as an example as well. So the question said, use your gradient and a suitable equation. So the gradient we already calculated, so don't go back to your table. There's the gradient, use it, and use it with its powers of 10 that you have there already. And then you substitute that value into the equation. In this one, the equation that was on the information sheet, the graphing question was in oscillations. I'm going to share that oscillations, or the graphing video with you that was at conference about last year's paper, about the graph specifically. But here you can see that was the equation we used because we've got x squared, and the question asked for the angular frequency. So that is why we knew we need an equation with the omega in it, and that you can go through the maths. But never ever did this memo go back to the table. You substitute it into the equation from your calculation that you've just had. And then please remember, if you got stuck somewhere calculating the gradient, stuck with time or anything, assume a gradient and then you can still use it in that final analysis question. In this case, because our graph went through the origin, we knew that we're not going to use an equation with a plus or minus in it. That's also a guide. And also, if you know that the equation you're using doesn't have a plus or minus in it, then that's also a good way of stating for you to know that the graph is going to go through the origin. Then the last thing, please, your calculator. In FS Physics, you are allowed to use your calculator to use your line of best fit. Please, I have loaded that calculation, or you can that video as well. So you can use your calculator for that line of best fit. You put the points in the data on your calculator and it gives you your regression line. It gives you the y-intercept. It gives you the gradient of your graph, because you would see that often we accept a range of values here for the answer. If you look back to memos of past papers, there's a range that is generally accepted. And I think that's that for analytical skills.